Hello, ladies and gentlemen. Welcome to the third part of this very large Unit 9 that we are working in. I'm just going to go through this front page right here. So depending on if you're Cohort A or Cohort B, you can see what the schedule is for the next couple of weeks. You can see that there's some days that are strictly going to be just lessons. There's some days that are going to be practice. And there's a couple in here that are lessons with homework attached to it. So you can see if you scroll down the calendar here, Cohort A students, you will be having your Unit 9 comprehensive test on Wednesday the 19th. Cohort B students, you will be having your Unit 9 comprehensive test on Friday, May 21st. All right, so if you're ever absent or anything, you can see exactly what it is we're doing on those days. So for today, we're going to start off with Lesson 14, which is actually just a lesson. So all you're going to do as your assignment is you are going to watch this video, you're going to fill in the notes completely, and you're going to send me a picture of your completed notes to show me that you actually did this. The day 15 is going to be a practice day based upon this. So if you finish this and you just want to jump right into day 15, that probably would be a great idea because day 15 is not going to have a new video. It's just a long practice assignment based upon what we're doing here in Lesson 14. All right, so we're going to start out here in Lesson 14, and we're going to be talking about, once again, arc relationships, but this time not with chords, or sorry, not with angles, but with chords. So we're going to be talking more about length of chords, length of radius, length of diameter, and that relationship with intercepted arcs. So we're going to step away from angles for a little bit and focus on length of segments inside the circle. So today we're going to see some properties, and you can see right off the bat here we're actually going to do a proof, something we haven't seen for a while. Everything in this unit comes full circle. This is a great unit to kind of end the year. It's not the last unit. We have one more unit after this, but the reason why we do circles at the end is because we tie in so many things. So the idea is, the theorem, is that if a radius is perpendicular to a chord, if a radius is perpendicular to a chord, then it bisects the chord. So if the radius is perpendicular to the chord, then it bisects the chord. All right? Or in reverse, the converse, if a radius bisects a chord, so if the radius splits the chord in half, then it's perpendicular to the chord. All right? So we're going to prove the original theorem itself. We're going to prove this down here. We're going to prove that if a radius is perpendicular to the chord, then it bisects the chord. And we're going to go back to triangle proofs way back in the fall. So we are given that line segment DE is actually the diameter of the circle, is perpendicular to AB, which is the chord. We're going to prove that AF is congruent or equal to FB. So this is where we start. This is where we're going to end. So we're going to start with our given. What do we get when two lines are perpendicular? That's right, we get right angles. So I'm going to call this angle 1, and I'm going to call this angle 2. And we're going to say angle 1 and angle 2 are, hold up, this is the given. I'm jumping ahead of myself here. Then the statement is that angle AFC, which I have called angle 1, okay, this is what I have called angle 1, and angle BFC, which I have called angle 2, are right angles. Why are they right angles? Because perpendicular lines create right angles. That's not new. That's from the fall, okay? That's not a new concept. So we have a right angle here at angle 1. We have a right angle there at angle 2. Now, what did we always say after we identified that we have right angles? Well, we always said that those right angles are equal, or those right angles are congruent, because all right angles are equal or congruent. So in this case, we're using equal. All right, so we got a pair of angles, okay? So we're trying to prove that these two triangles are congruent so that we can use CP-CTC. Now remember, to prove triangles congruent, we have side, angle, side. We have side, side, side. We have angle, angle, side. We have angle, side, angle. And we have HL. So we're trying to create one of those five. So right now, we have a pair of angles. We have a pair of 90-degree angles. All right, so what else do we have? FC equals FC. Well, this is something we saw a lot. You should know what that is. That's reflexive sides are congruent, or reflexive sides are equal. Reflexive sides are equal. So we have a pair of angles. We have a pair of sides. Okay? What else do we have? AC equals CB. AC equals CB. Now, why are those two the same length? Well, you're probably looking at the diagram and you should be, oh, those are both a radius. And so no matter what radius I draw, it's always going to be the same length. So I can connect C to any point on the circle, and they're all going to be the same length. So all radii in a circle are equal. All right. So it looks like we have a pair of 90-degree angles. We have the reflexive side, and we have these radii that are equal. So we have a pair of angles and two sides. Aha, it must be side, angle, side, right? Well, no, because the angle is not in between the two sides. Oh, it must be angle, side, side. Well, no, because angle, side, side is not one of the ones we're allowed to use. So what do we have? We have two right triangles. The reflexive sides are legs, and the radii are the hypotenuse, so we are using HL. So in order to use HL, we need to identify that we have right triangles. How do we know that they're right triangles? Well, because each triangle has a right angle. And now we can say the two triangles are congruent, because hypotenuse leg of one triangle is congruent to the hypotenuse and leg of the other triangle. And now, using something we haven't used for a while, we can say that this line segment AF is congruent to this line segment FB, because corresponding parts of congruent triangles are congruent. So there's a nice little proof that shows us that if a radius or a diameter is perpendicular to the chord, it's going to bisect the chord. Okay? So if a diameter or a radius is blank to a chord, it bisects the chord. If a diameter is perpendicular, it bisects the chord. If a radius is perpendicular to a chord, it bisects the chord. So it's the same sentence two times in a row. I changed where the blank was, and I just changed diameter to radius. It's the exact same sentence. I just changed where the blank was. If a diameter is perpendicular to the chord, or if a radius is perpendicular to the chord, it bisects the chord. The perpendicular bisector of a chord always contains the blank of the circle. The perpendicular bisector of a chord always contains the center of a circle. In other words, if I were to draw a circle and then sketch a chord, okay? If we did the perpendicular bisector of construction of this chord, so we opened up our compass and we went like this and we went like this, this right here is going to go through the center of the circle, all right? Because this is going to be the same as this. That's going to be the diameter or a diameter of the circle. So the perpendicular bisector of a chord always contains the center of the circle, because the perpendicular bisector of the chord is the diameter, or a diameter, because there's many diameters you can draw. All radii of a circle are congruent or equal, whatever word you want to say there. Okay? All right, so let's do a couple practice with this idea so you can see what this looks like. All right, so in number 1 here, part A, C is the center of the circle, so that means that this line segment from up here down to this dot is part of the entire diameter. And the diameter is perpendicular to this chord, which means it's bisecting the chord. So if the entire chord is 24, that means that this side is going to be 12 and this side is going to be 12. So what is AC going to be? Well, AC is the radius, and we have a little right triangle here where the radius is unknown. 5 is a leg, 12 is a leg, and then X is that line segment AC. 5 squared plus 12 squared, you should have your calculator out. 5 squared plus 12 squared, that's 169. The square root of 169 is exactly 13. So the radius of this circle is 13. All right. B, the radius is 6. This thing right here, if I drew it all the way through, that would be a radius. And it's perpendicular to this chord. So it's bisecting the chord, so those two are the same. So this is going to be 6 right here. So if I call this piece X, now we're doing leg squared plus leg squared equals hypotenuse squared. So 36 minus 9 is 27. So X is equal to 27. X squared is equal to 27. So X is equal to the square root of 27, which when you simplify that, well, what times what is 27? Well, that's 9 times 3. Square root of 9 is 3, so this is 3 radical 3. So half of this chord is 3 radical 3. The other half of the chord is 3 radical 3. So when you add those two together, 3 plus 3 is 6. You do not add what's underneath the radical, so it's just 6 radical 3. All right, last one here. We have a diameter that is 20 centimeters long. So that means that this piece is 10 and this piece is 10. We have this thing, which is a radius. It's kind of been cut short. The radius is perpendicular to this chord. So this is the same as this. And all we want is this piece over here. So leg squared plus leg squared equals 10 squared. All right. So x squared equals 100 minus 75, or minus 25, which is 75. So the square root of 75, you simplify that radical. If I'm going too fast, remember you can always rewind and rewatch this. Or you can just pause the video so you can write this stuff down. So x squared is 75. X is the square root of 75. Well, what times what is 75? Well, that's 25 times 3. And the square root of 25 is 5, so that's 5 radical 3. So this half of the chord is 5 radical 3. The whole chord would be 10 radical 3. So those are just a couple examples using the idea that when a radius is perpendicular to a chord, it is bisecting the chord. All right? So that's the first property of today. All right. Next one. In a circle, if two chords are congruent, then the center is equidistant from the two chords. Or the converse. In a circle, if the center is equidistant from two chords, then the chords are congruent. Basically, if this chord is the same length as this chord, then the distance to the center of the circle in a perpendicular line is going to be equal. The shortest distance between 2 points, between a line and a point, is that perpendicular line. So if I draw, so in other words, if I draw a circle and I draw 2 chords that are the exact same length, then their distance to the center is going to be equal. That's the idea. Okay? All right, let's see an example of this. All right, here we have a chord that's going to be this whole thing. We have a chord that's this whole thing, and we can see that their distance to the center is the same. So that means that this entire chord and this entire chord are going to be the same length. All right, so how long is this entire chord? Well, if I extend this, now we're going to combine ideas here. This would be a radius. It's perpendicular. So this entire thing would be 5 plus 5, which means this is 10. And therefore, if it's the same distance to the center, this is the same as that, then this whole thing is also going to be 10, and therefore x is going to be 5. All right? So it kind of ties in the first property as well, because that distance to the chord is always going to be a perpendicular segment. All right? So if these 2 chords are the same length, then these 2 distances to the center are also going to be the same length. All right? All right, last page. Now, we kind of already saw this one in some of the review because it's pretty basic. In a circle, congruent chords intercept congruent arcs. In a circle, congruent arcs intercept congruent chords. So if 2 chords are congruent, the arcs that they intercept are also congruent. Okay? In a circle, congruent chords define congruent central angles. In a circle, congruent central angles define congruent chords. Basically, if 2 chords are congruent, the central angles that open up to those 2 chords are also going to be congruent because those arcs are congruent. So this would be x degrees. This arc would be x degrees. All right? If this is x, then this arc is x degrees. So, for instance, let's say that this angle here was, I don't know, 55 degrees. Well, this angle here would also be 55 degrees because this radius is the same as this radius. So 55 plus 55 would be 110, so this would have to be 70. So this would be a 70-degree arc. Now, if this is the same as that, then this would also be 55, and this would be 55, and this would be 70, and that would be 70 as well. All right, so let's look at an example of this. So here we have 2 arcs, or two line segments. Line segment AD is congruent to line segment DE. Okay, so 2 chords are the same length. So that means that this central angle, let me call this C because that's the center of the circle. ACD is congruent to central angle DCE. And therefore, if those 2 central angles are congruent, arc AD is equal to arc DE, which means x plus 16 equals 5x, which means 16 equals 4x, which means x is equal to 4. So this would be a 20-degree arc. This would be a 20-degree arc. This would be a 20-degree angle. This would be a 20-degree angle. And let's see, 180 minus 20 divided by 2. So all of these little angles here would be 80, 80, 80, and 80, because they're all the base angles of the isosceles triangles. All right, and the last one here. In a circle, parallel chords intercept congruent angles. So basically, if 2 chords are parallel, then the arcs in between them are going to be the same measure. So I'll draw another one for you. So if I draw 2 parallel chords, then the rule says that this arc here and this arc here are going to be the same. That's it. That's what the rule says. All right? If the measure of arc UT is 30 degrees, then what's the measure of arc UV? Well, let's see. This is going to be 30. Those are parallel, so that tells me this has got to be the same as this. This is identified as the center, so this half of the circle is 180. This half of the circle is 180. So 180 minus 30 leaves me with 150. So those two are the same, so divide that by 2 means that this has got to be 75, this has got to be 75, and this has got to be 180 down here. Okay? So just to extend to what we talked about, so if this arc is 75 and I connected them with a line segment, and this arc is 75 and I connected those with a line segment, those two line segments would be the same length. And then we can get into the angle stuff, all right? So a lot of this kind of works together, all right? So this is the end of lesson 14, all right? So your assignment now is to turn this in to show that you actually watched it and filled in. So your next assignment is to do lesson 15, all right? And it's going to utilize all of these properties we just talked about. So I would honestly recommend that you do the lesson 14 practice right now because everything is fresh in your head, all right? And when it asks you to identify which theorem or which property, I want you to write these out in full like you see them here. Not like just 2 words, but if it says, if a diameter of a circle bisects a chord, then it must be perpendicular to the chord. So if you're using that property, write it out. If you're using another property, write it out. This is why I separated this into 2 days. So you have plenty of time to write out these properties in full. So you're going to see there's a lot of these. Identify the property, which theorem or property, all right, which theorem or property, justify your response, that's a theorem or property. All right, anytime it says that, you're going to fill that in. Justify your response, justify your response, justify your response. So anywhere it says to justify your response or to identify the theorem, you're going to come back to here and you're going to pick which of these you're using and you're going to write it in. If you don't write them in, you are going to get very few points on the homework. This is going to be probably homework worth about 12 points or so. And if you don't write them in, you're going to be lucky to get half of the points. So half of this homework is going to be you taking the time to write these properties in, all right, when you do lesson 15. All right, thank you guys for watching. If you have any questions, please let me know. Have a great day.